I also had not figured that one out, so.
Okay. Number 36 from chapter 7. Okay, let's see. Chapter 7 is huge. Let's see. Was this one that says that let X be the number of ones and Y the number of twos?
Yes, yes.
That occur in n rolls of a fair die. And then we are asked to compute the covariance of those two.
Yes.
Yeah. Okay. Well, let's see here. Let me do this. Okay. Hey, 199 pages. Doing good here. So X. Okay, so we have n rolls of a fair die. So oops, let me not use that color. That's a little hard to see. So n rolls of a fair die. Okay, X is equal to the number of ones. Y is equal to the number of twos. My inclination is to write this as a sum of indicators, right? So, you know, 1 of A1 plus indicator of A2 plus ... plus the indicator of AN. Okay, where how do you think I'm going to define AI? What do you think the ith event is going to be, right? X is supposed to be counting the number of ones. What do you think the ith event AI is going to be in this context?
Is that going to be re-roll a 1 on the I roll?
Yeah. So 1 on roll I. Yeah. And Y is going to be the indicator of B1 plus the indicator of B2 plus ... plus the indicator of Bn, where Bi is the event 2 on roll I. Yeah? Okay. So, well, what do you guys think? Okay, I mean, that seems to be the most natural definition of X and Y in terms of sums of indicators, which seems to be, you know, it seems to be the scaffolding upon which chapter 7 is built, right? So for sure, do you guys, you know, like it's pretty easy to compute the expected value of X. Okay, that's going to be the sum I going from 1 to n, the probability of these AIs. But of course, those probabilities are all the same. You know what I'm saying? And by the way, I mean, look, just to look, is rolling a 1 any more or less likely than rolling a 2 on a given roll? No. So this is actually going to be the same as the sum I going from 1 to n of the probability of these BIs, right? And what is the probability of AI?
1/6.
Yeah, it's that easy. Same thing for the probability of BI. So, I mean, all of this to say that the expectations of X and Y are just the same. Okay? And it's just going to be n over 6, right? So the expected value of X, because each one of those summands is a sixth, you end up getting n over 6, which is the expected value of Y. Okay, so that's part of the way toward computing the covariance, which is our ultimate goal here. What's the other thing that we need? What do we also need? Expected value of X, Y. Yeah. So, that's interesting, right? Because the covariance of X, Y is going to be the expected value of product of X and Y minus the product of the expected values, right? So what do you guys think about that? By the way, which problem? This was 7.36, right?
Mhm.
Okay. So what do you guys think about the expected value of X, Y? Is that a sum of indicators? Well, I mean, yes, it is. It is a sum of indicators. But okay, what indicators is the question. So look, if I multiplied X and Y together, do you see that that's like multiplying a bunch of indicators together, right? Because X is a sum of indicators, so is Y. If I multiply X and Y together, it's going to be, once I expand out the product, it's going to be a sum of indicators, yeah? Oops, what's that? Sorry about that. Let me cast this thing again. Okay. I think it should be coming here pretty soon. Okay. So what do you guys think? What's XY equal to? Isn't it just like the sum over all possible I and j of the indicator AI times the indicator of bj? Yes? Isn't that exactly what would happen if we happen to multiply out these two sums of indicators? Yeah? But actually a lot of things kind of disappear. Oh, and by the way, this is the same thing as the sum over all possible I and j, the indicator of, so that thing right there is going to be 1 if and only if both AI and BJ happen. So that is the indicator of the intersection of those two events. So it's the indicator of AI intersected with BJ, okay? Now here's the thing. There are some things that we can actually eliminate from this. I'm excited to go to page 200 here, so here we go. All right, so let me just rewrite this. XY equals the sum over all possible I and j, indicator of AI intersected with BJ, okay? Now there are some of these indicators that basically I can throw out because they are always zero, always, okay? They are always going to be zero. Which ones are always zero?
The ones where I equals j.
Yeah, right. So let me kind of rewrite this sum. I'll write it as the sum overall I going from 1 to n, the indicator of AI intersected with BI, plus the sum where I and j are different, the indicator of AI and BJ. Okay. And what are you saying, Katie?
So that first sum you have there will have to be 0 because either AI, like either we have a 1 on the roll or we have a 2, but they're not both going to happen on the same roll.
Yeah, right. You can't have, right? So the key here is that 1 and 2 can't happen. That'd be really weird, right? Can't happen simultaneously. Okay. So that's why that thing ends up being 0. So in other words, let's just rewrite this. XY, just trying to write this as simply as possible, really is just the sum over I different from j. So by the way, what this kind of tells us is that the A's and the B's, the A's themselves are independent among themselves, right? A1, A2, etc. The B's are independent among themselves, but it looks like that we have some dependency going on when we cross over from the A's to the B's. Yeah, seems to be some dependency arose whenever we looked at events with the same index. Okay, but this is I different from j, indicator of AI intersected with bj. Okay. Okay. So looks like I just need distinct pairs of indices. How many summands are there here? Just to make sure we're keeping track of things. Up here, let me just say that there were n squared pairs, right? Right? There were n options for I and there were n options for j. How many possible pairs do I have here? What do you guys think?
N squared minus n?
Yeah, n squared minus n, which is the same as n times n minus 1, if you think about it, right? Yeah, right, which is, so n squared minus n pairs. Okay, and what about the probability of like, so for instance, what if I computed something like the probability of A1 and B2, all right? Is that going to be any different from like A5 and B1, for instance? No, they're all the same, right? Okay, so when I go to like compute the expected value of this, I really only need to compute the probability of one of these things. Okay, so what is the probability of A1 and B2? So that means literally A1 is I got a 1 on the first roll. And B2 is I got a 2. I mean, it's just coincidence that the indices match up, right? In fact, let me tweak this. Let me do A5 and B3, just so you don't get confused here. So A5 is the event where I got a 1 on roll number 5. B3 is the event where I got a 2 on roll number 3. But those are, what's the key? What's the key term? Those events are
Independent?
independent. We're on the 5th roll for the one thing, and we're on the 3rd roll in the other one. So it turns out that the only dependencies arise when the indices match. Yeah, that's it. So what's the probability that happens? The probability I get a 1 on the 5th roll and a 2 on the 3rd roll. What's that probability? One-sixth times 1/6. Yeah. So let me just say it's, 1/6 squared. Therefore, do you see that we're going to be able to fairly easily compute the expected value of this product? Yeah. And they're all going to be the same probability of occurring. So I just have n times n minus 1. And then I have this probability here, which is 1/6 squared. That's kind of interesting. Okay, so what's the covariance of xy going to be? Well, it's going to be the expected value of xy, which is this little, this little thing right here. And then I subtract off the product of the expectations of x and y, and those were the same, weren't they? So wasn't that like n squared times 1/6 squared, which, by the way, I could factor out n times a 6th, I guess. N times a 6th. What's left behind? Well, there's an n minus 1 times a 6th minus another n times a 6th. Hey, check this out. This is 6th. If I kind of distribute it through right here, this guy is going to cancel completely with this guy. And I just get negative 1/6. Okay, I'm just going to get negative 1/6. So overall, I get negative n times 1/6 squared. Is that right?
Mm-hmm.
Yeah?
Yep.
Interesting. What does that tell you is going on correlatively with these two things? I mean, to get the correlation coefficient, I said that you have to divide the covariance by the product of the standard deviations of these two things to kind of get it in the range from -1 to 1. But the standard deviations are always positive. You know what I'm saying? So when I divide the covariance by those, I'm still going to end up with something that's negative. Okay. So what can you say about correlation? Are they correlated? Yeah. There's a slight negative correlation between the two. And let's think it's a slight negative. I don't know. It's slight negative correlation. So, I mean, here, hang on a second. We could actually, let's go a step further here. Back on to 201. Okay. So what about the expected value of x times x minus 1? That's going to be 2 factorial. We came up with a formula for this for sums of indicators, right? It was 2 factorial times the sum over I less j, the probability of AI intersected with AJ. Yeah? Remember we came up with a formula for that for like following factorial moments for these sums of indicators? And what's this probability? I less j, what's this probability going to be right here? Oops, I didn't mean to highlight that entire thing. What's that probability going to be?
Isn't it still just going to be 136?
Yeah, 1 over 6 squared again. 1 over 6 squared again. And it's I less j. Well, so how many pairs of indices are there here? What do you think? Isn't there just n choose 2 of them? Yeah? N choose 2 things, and then it's going to be 1/6 squared, right? And if you think about this for a minute, the 2 factorials basically cancel, and you're just going to end up with n times n minus 1 times 1/6 squared. Okay. So what's the variance of x? Well, of course, that's the expected value of x squared minus the expected value of x quantity squared, which is going to be, you know, basically the expected value of the second falling factorial moment plus the expected value of x minus the expected value of x squared. Okay, which is what? It's just going to be n times n minus 1 times the 6 squared. What did we get? N over 6 minus n squared, or n over 6, right? N squared over 6 squared. Okay, I think that you can pull out n over 6 from all of these. Okay, and what's going to be left behind? N minus 1 times the 6th plus 1 minus n over 6. Okay, and if you distribute this guy through here, this positive n over 6 and this negative n over 6 cancel. You get 1 minus a 6th. Okay, so this is n times a 6th times 1 minus a 6th. Hey, this looks a lot like the binomial. And that kind of makes sense, doesn't it? Think about it. We're basically counting the number of successes that this thing had in rolls of the die, right? So for x, we were counting the number of, for x, we were simply counting the number of ones that rolled. So if 1 is a success, that's what's happening, okay? And by the way, you guys realize that this is going to be the exact same thing as, why would that be any different from the variance for y? It has to be the same. We're just changing our thinking from rolling 1s to rolling 2s. Make sense? The reason I'm doing this is because now we can actually compute the correlation coefficient. Okay? So what is rho of xy? Well, the formula says it's covariance of xy over sigma x sigma y. What did we get for the covariance again? Can someone remind me?
Negative n over 36.
Okay, negative n over 6 squared, basically.
Yeah.
Okay. Or just a sec. Yeah. Okay, so you said negative n over 6 squared.
Mhm.
Over, what did we get for this other thing? I mean, if I multiply these two things together, it's just basically going to be the variance again, isn't it? Both of these standard deviations are the same. So we're just going to get, we're just going, we're just going to get the variance again. So this is going to be n times the sixth times 5/6. Okay. So the n's cancel. What else cancels? Well, I guess both of the 6's cancel. Yeah, and what do I end up with? Like negative a fifth, right? So I have a correlation of negative a fifth. So I have a, looks like a slightly negative correlation in this case, which means if I have a high number of 1 rolls, so a high number means like more than the average. If I have a high number of 1 rolls, then I will have, remember that negative correlation means they tend to live on opposite sides of their means. Yes? So if I have a high number of 1 rolls, that will tend to result in what? A high or a low number of 2 rolls?
Lower number of 2 rolls.
A low number of 2 rolls. Doesn't that make sense? Think about it for a minute. If I have a massive number of rolls of 1, then I'm not going to have a lot of room for 2 rolls. It just doesn't seem very likely that I'm going to end up with a high number of both of these. Does that make sense? Seems like if I have a high number of 1, that's going to force a low number of the other. Yeah? So it makes sense that these two things would actually end up being negatively correlated. Okay? It's a great question. And I think it sort of illustrates a lot of the stuff that we've been doing. So that's a good one. Does that make sense, Emma?
Yes.
All right. Well, what else? Sort of satisfying. What else? Anything else?
Talk about problem 21 in chapter 7.
Okay. So what were you thinking on this, Katie?
Well, so I think I was trying to set it up as a sum of geometrics, but it wasn't working, so probably not what I was supposed to be doing.
What were you thinking about? So we have 100 people.
Mm-hmm.
It says find the expected number of days of the year that are birthdays of exactly the number of days of the year. The number of days of the year. Okay. Yeah. The number of days of the year that are birthdays of exactly 3 of the 100 people. Yes?
Mm-hmm.
So no horsing around. I can't have less than 3 and I can't have more than 3. Okay. So, I mean, shouldn't we write X? So if X is the number of days, okay, so if I let X equal to the number of days
Mm-hmm.
that are B days of exactly 3 people among 100. Can't we write X as a sum of indicators of some kind?
Mm-hmm.
What? What indicators?
Well, I think the way I was trying to do it, and I think I may have been overcounting, but was basically like you've got a bunch of like groups of 3 people. So it would be 1 if like the people all have the same birthday and 0 if they don't. But I think that that misses something in there with the exactly 3 people. So I'm not quite sure that's the way to go.
Yeah, because if you do that, yeah, my inclination would be to have an indicator on a particular day.
Okay.
Does that make sense?
Mm-hmm.
So it's going to be 1 sub A1 plus 1 sub A2 plus 1 sub, okay, let's not be, overly complicated here and think about leap years. But there are going to be 365 of these events, where what is AI? What is AI? It's the event that there are exactly 3 people have a birthday on day I. Does that work? Yeah? So day 1 is like January 1st, day 2 is January 2nd, etc. Right? Okay. What's the probability of AI? And by the way, let's just do the probability of A1. What's the probability that exactly 3 people have a birthday on January 1st? Any ideas?
This could be completely and totally wrong, but could we like choose 3 people out of 100 and then multiply it by like 1 over 365 to the 3, and then like multiply it by 300 and something else divided by 365, like the rest of the days to like the 97. So like those people aren't on January 1st. Could you do something like that, or is that like no
So
good?
you're thinking of using kind of like the binomial distribution?
Yeah.
Basically go to, right. So you basically are going to go to each person. I mean, so one thing you could do, I mean, to make this exceedingly clear, you could let Y be binomial. Oops. Are you guys all right? Okay. We could say Y is binomial with N equal to 100. These are the people. Okay. And proportion of success. So I don't know. So I'm going to say Y1. Okay. Because Y1 is like going to correspond to A1. So it's going to be binomial with N equal to 100 and proportion of success equal to 1 over 365. Yes? Then what Emma is suggesting is that the probability of A1 is really just the same as the probability that Y1 equals what? What are you thinking, Emma? The probability that Y1 equals... So here you're thinking of the people as being independent trials, right?
Yeah.
First person, and you say, hey, were you born on January 1st? You know, yes or no? And you just go to each one of those. And you want that to be successful exactly how many times?
3 times.
3 times. Yeah, that's exactly right. And we know stuff about the binomial. Know what I'm saying? Okay, we know a lot of stuff about it. This has to be the right approach. I mean, like all this stuff is coming out that we know well, right? Okay, so what is this going to be? You said it was n choose 3 or 100 choose 3, right?
Yeah.
And then what?
And then 1 over 365 to the 3.
Third?
And then
Yeah, 364 out of 3 over 365 raised to the?
to 97.
Exactly. And is that going to be different for any of the other A's? I mean, was there anything special about the first A? No, that's the probability of AI for all I. Okay. So can we compute this expected value now? Page 2 and 3. The expected value of X is going to be equal to, look, it's going to be the sum of those, the expected value of the sum of those indicators. So it's going to be the sum of those probabilities, correct?
Mhm.
And so I think that we're going to get 365 times those probabilities. N choose 3 times 1 out of 365 raised to the third. Oops. 364 out of 365 raised to the 97. Yeah. And I think if you think about that, that expectation actually makes sense. What we did is we go to each one of the days. There are 365 of them. And you say, well, I need a 3-tuple of people, all of which have the same birthday, the birthday on that day. Okay. But then I don't want anybody else to have a birthday on that day, which is where the 364 over 365 raised to the 97th comes from. Okay. So there you go. Is that the answer?
I think they gave the answer in like a decimal.
What?
I think so.
It works
You
out to
said
the
N.
answer.
What's that?
It works out to the answer in the
Would
book.
N just be 100?
Yeah, that should just be 100. Sorry. Okay. So this is 7.21. Okay. What was the second problem?
Number of distinct birthdays.
The expected number of distinct birthdays. Well, what do you think?
I mean, I could be missing something, but it seems like it ought to be very similar to the one we just did. Just we don't want
Okay.
as in 3 people on a birthday, we just want 1. But there could be some other factor I'm missing.
Well, the expected number of distinct birthdays. The expected number of distinct birthdays. So what if everybody, so what would be the value of this random variable So first of all, I mean, let's just think about what is the range for this? Well, clearly, if everybody had the same birthday, uh, you know, then this would be 1, right? Okay, and if everybody had a birthday either on January 1st or January 2nd, that thing would be equal to 2. But if all 100 people had different birthdays, this would be 100, right?
So it's asking how many possible birthdays are there, not how many birthdays have only one person.
Yeah, I think so.
Okay.
It just wants the number of distinct birthdays.
Okay.
Yeah.
I was confused on that then.
So what do you guys think? Hmm. What do you guys think? Any ideas? Is there some way to like use indicators to help us with this?
Is there a way that we could, instead of looking at when everybody has a distinct birthday, do 1 minus the probability that everybody is on the same birthday?
Well, yeah, something like that is what I have in mind, yes.
Okay.
It has to do with expressing the random variable in that way.
Okay.
So, I mean, I think, so let's see here. So is it just, can you just say that, can you make an indicator for each person? Well, hang on. Yeah. So could it, is it just, okay, so I mean, this is kind of strange, but I think it actually works. So I think you can write D equal to 1 plus the indicator, you know, B1 plus the indicator of B2 plus dot, 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 plus, oh man, is that right? And what I was trying to do was write an indicator for each person that basically is 1 or 0 based on them having their own special birthday date. Okay? Does that make sense? So that if B1 or if person number 1 had their own birthday, that should contribute 1 to this. Or wait, is it just the sum of these things? Okay, indicator of B 100. Okay, where what is BI? This is the event that person I has a unique birthday. The only thing that makes me nervous about that is how would you get 1 from this? Does that make sense? Because the number of distinct birthdays. Oh, wait. No, this isn't what we want, is it? Because, for instance, we want to count things. We want to count things like if person number 1 and person number 2 have the same birthday, we would want to count that, right? That would be one of our distinct days. So this isn't quite right. But is there something that we can do that's kind of like this? Help me out here. So what were you saying, Emma, again?
I can unmute myself. I was just thinking we could handle it in a similar way to the previous one, except we're looking at when it's 1 minus the probability that they're all on the same birthday, or rather it's like the probability that they're all the same birthday is going to be 1 minus like 364 divided by 365 to 100. And then there's like 365 of those, maybe. I'm not entirely sure. I'm just thinking out loud here.
Yeah, there has to be a way of writing this as a sum of indicators.
Okay.
Yeah, but I think that something like that is probably going to work. It's just a matter of kind of seeing it the right way. But let me think about that. I'll get back to you guys. Maybe I'll post like a little video or something. But yeah, there's got to be a proper way to look at this so that it just easily. I mean, it can't be like if it starts getting out of control hard, that something is going wrong. Okay. So I can imagine in my mind, I almost took this sum that I wrote right here and tried to like square it and raise it to higher and higher powers. And I think that would work, but that has to be not correct, okay? Or, I mean, it might be correct, but it has to be way harder than it needs to be. So let me just think about that, okay? And I'll definitely get back to you on that. All right? Well, anything else? Well, hey, thanks for bringing the heat. That's good. I like it when people come and ask good questions, and those were good questions for sure. Hey, don't forget that I think everybody in this room has actually already turned in their sum projects, so that's great. Okay, but I will actually send out a little homework quiz for you to work on. Probably middle of this week, I'll send that out, and that will be the last official thing that you'll do. Okay. Well, let me think about this problem. I'll definitely get back to you on that. Okay. All right. Enjoy your day.
Thank you, Dr. Hammett.
Thanks, Dr. Hammett.
See ya.